Hello, friends, and welcome back to Webronaq. Here is a question. Imagine you have a collection of items and you need to visit every single one of them, in order, without missing a single item. How do you do that? That idea has a name. It is called traversal. Traversal simply means moving through a data structure and visiting each element, one by one, and it shows up everywhere in programming. Searching for a value, printing a list, calculating a total. In this video, we are going to build a clear mental model of what traversal is, why it matters, and how it works across different data structures. We will follow one simple idea the whole way through. Let's start where it is easiest to see, a plain integer array. All right, let's make this concrete. We have an array holding 5 integers. 10, 25, 7, 42, and 3, stored at index positions 0 through 4. Traversal here means visiting each element, one by one, in order. We start at index 0, read the value 10, then move to index 1, read 25, then index 2, read 7, and so on until we hit the last index. The index variable is our position tracker. Every loop iteration, it increments by 1, and we use it to access the next value. Nothing is skipped, nothing is repeated. That trace table on screen shows exactly where we are. I equals 2, value is 7, 2 steps done, 2 more to go. The rule is simple. As long as the index is less than the length of the array, keep going. Up next, we swap this index for a pointer and see how traversal works on a linked list. All right. Now let's take that same idea and apply it to a linked list. With an array, we moved by incrementing an index. A linked list works differently. There are no index positions. Instead, each node holds a value and a pointer to the next node in the sequence. Here we have 3 nodes, storing 10, 20, and 30. To traverse this list, we start at the head node. That's our entry point, and we follow the pointers one by one. We land on 10, read it, then follow the arrow to 20, read it, then follow the arrow to 30. When we reach the node whose pointer is null, we know we're done. The movement is pointer-based, not index-based, but the core idea is identical. Visit every node in order exactly once. Next, we'll see how traversal changes when a structure branches into a tree. All right, now let's move from our linked list over to a tree. And things get a little more interesting here. With a linked list, there was only one path forward. A tree has branches, which means you have to make a choice about which order to visit the nodes. That choice is called a traversal order. The clearest one to start with is in-order traversal. The rule is simple: left, root, right. Visit the left child first, then the current node, then the right child. Here's the interesting part. On our small 3-node tree, with 10 on the left, 20 at the root, and 30 on the right, in-order traversy visits them as 10, then 20, then 30. Perfectly sorted. Next, let's talk about what all of this traversal actually costs. All right, now that we have seen traversal on an array, a linked list, and a tree, let us talk about what it costs. Every time you traverse a structure, you visit each element exactly once. No skipping, no shortcuts. If your array has 10 items, you make 10 visits. If your linked list has 500 nodes, you make 500 visits. That relationship is linear. Double the size, double the work. That is big O of n. It holds for all 3 structures we have covered. The tree is the same story. 7 nodes means 7 visits, regardless of which traversal order you choose. The shape changes, but the count does not. 1 visit per node, every time. That is the cost of traversal. Simple, predictable, and honest. In the final slide, we will tie everything together into one clean rule. All right, let's bring it all together. We covered 3 structures throughout this video: arrays, linked lists, and trees. Each one stores data differently, and each one asks you to move through it differently. But here is the rule that ties them all together. Traversal always means visiting every element exactly once. That is it. Whether you are stepping through array indices, following arrows in a linked list, or branching through a tree, the goal never changes. And as we saw in the last slide, that process costs big O of n, linear time, because the work grows with the number of elements. That one idea unlocks how you think about loops, recursion, and algorithms at every level. Keep it in mind, and it will serve you well. Thanks for watching, friends. See you in the next one.